Welcome to examples of systems with n linearly independent eigenvectors. So recall if y prime equals a times y has a with eigenvalues lambda 1 through lambda n, and n linearly independent eigenvectors xi 1 through xi n with xi I paired with lambda I, then the general solution is y is equal to c1 times xi1 e to the lambda 1t plus all the way up through cn times xi n e to the lambda nt. So we are going to use this trick to solve a couple 2x2 systems. In the next video, we will look at 3x3 systems. So let's consider the system y prime is equal to the matrix 5, -2 as the first row, 4, -1 as the second row, times y. Our job is to find the general solution. So the first thing we need to do is find the eigenvalues of the matrix 5, 4, -2, -1. So to do this, we do the determinant of 5 minus lambda, -2, 4, and then -1 minus lambda. So this is our matrix that's acting as A minus lambda times the identity matrix. So we just subtract lambda from the diagonals, and then we're taking this determinant. This is equal to 5 minus lambda times -1 minus lambda minus -2 times 4. So we are looking at, we would have lambda squared, then we would have -5 lambda plus lambda for a -4 lambda. Then we would have a -5 from the fact the multiplying or distributing out our 5 minus lambda times -1 minus lambda. And then we would have -8 or +8. So -5 plus 8, we're looking at +3. Eigenvalues, this is when it's not equal to 0. So eigenvalue occurs when this is equal to 0. So we have lambda -3 times lambda minus 1. This is set equal to 0. And we wind up getting that lambda is equal to 1 or 3. Next up, we need to find the eigenvectors. So we want to find the corresponding eigenvectors. So I need to give myself a little more space, 1 moment. So to find the eigenvectors, we're going to have to do this for each of our eigenvalues. So we'll first for lambda 1 equaling 1. So we are essentially solving the system. We take our original matrix with our minus lambda I. So we'll do 5 minus lambda, or 5 minus 1. Then -2, 4, and then -1 minus lambda. So -1 minus 1. And we're solving for a non-trivial solution to getting 0. My screen didn't update when I gave myself more room. I apologize. Okay, now we've got room to go. So we are looking at, this becomes -4, -2. Sorry, +4, -2 up top. And +4, -2 down below. And then of course 0 is on the right. And this simplifies to 2, -1, 0 for our first row, and the 2 rows just cancel each other out for a free variable for our second row. So we have the essentially 2 times xi1 minus xi2 should be equal to 0. So we get xi, we could take xi2 to be just 2 times xi1. So we will pick xi1 to be 1 and xi2 to be 2. And if we pick xi1 to be 1, then it forces xi2 to be 2. This then leaves us that we have our y1 would be the vector 1, 2 times e to the lambda here was 1, so we just have e to the t. Again, I need to give myself more space. For lambda 2 equaling, what was our other lambda? Lambda 2 equaling 3. We have the matrix 5 minus lambda, so 5 minus 3, followed by -2. Bottom row we have 4, and then -1 minus 3. And then we are looking for the solution that will give, or the vector that we can multiply by to get 0, 0. So we are looking at 2, -2, and 4, -4. So 2, -2, and then 0 for the first row in our augmented matrix, 4, -4, 0 for the second row. This simplifies to 1, -1, 0 for the first row. And then the 2 rows cancel each other out. For a free variable, we just get 0, 0, 0 for our second row. This tells us that xi1 and xi2 are equal to each other. So we'll just pick xi1 to be 1, and we have xi2 is also 1. So this gives us that our y2 would be the vector 1, 1 times e to the 3t. And we have general solution y is equal to c1 times, we had 1, 2 e to the t plus c2 times 1, 1 e to the 3t. So this is how we can go about finding our general solution. Let's go ahead and do one more example. We'll go ahead and solve the IVP. Y prime equals first row 3, 5, second row -2, -8 times y, with the initial condition y of 0 is equal to the vector 7, 4. So first thing we need to do is find the general solution. And in order to find the general solution, we need to find the eigenvalues. Again, what we want here is we want the determinant of 3, 5, -2, -8. Sorry, that matrix minus our lambda times our identity matrix. So 3 minus lambda and then 5 for our first row. And then -2 and -8 minus lambda for our second row. We want this determinant to be equal to 0. So we are looking at 3 minus lambda times -8 minus lambda minus 5 times -2. We want this whole thing to be equal to 0. We therefore get lambda squared. Then we have plus 8 lambda minus 3 lambda would be plus 5 lambda. And we have a minus 24, and then plus 10 would be minus 14. So lambda squared plus 5 lambda minus 14 equals 0. This factors as lambda plus 7 times lambda minus 2 equaling 0. So we got lambda 1 is -7 and lambda 2 is 2. Once we have our eigenvalues, the next thing we need to do is find the eigenvectors. So again, for lambda 1 equaling -7, we are looking at the augmented matrix, 3 minus -7 and 5 for our first row, and then -2 and -8 minus -7 for our second row, and then the augmented part will be 0, 0. I need to update my screen. All right, so we have 3 minus -7, 5, and then augmentation 0 for the first row, -2, -8 minus -7, augmentation 0 for our second row. So we are looking at 10, 5, 0 for our first row, -2, -1, 0 for our second row. Or reducing, we have 2, 1, 0 for the first row. And then the two rows just cancel each other out. We do get a free variable. So we have the psi2 should be equal to -2 times psi1. I apologize, my screen's not updating today. All right, we'll try this approach today. So we've got psi2 is equal to -2 times psi1. So this vector, we have psi, we can take to be, so we'll pick our vector psi to be, we'll pick 1 for the first position, and the second position would have to be -2. And this was finding our first vector. So this is our vector psi1. And we have y1 is 1, -2 times e to the -7t. Now we do the same thing for lambda 2. Lambda 2, I believe, was equal to 2. Yes. So we will do 3 minus 2. And then 5, 0 for our first augmented row. Then we are looking at -2 and -8 minus 2, 0 for our second augmented row. This simplifies to 1, 5, 0 for the first row, and -2, -10, 0 for the second row. This further simplifies to 1, 5, 0 for the first row, and 0, 0, 0 for the second row. As the two rows are dependent, we can cancel them out. We wind up getting that we have xi1 is equal to -5 times xi2. So we can go and pick our vector xi2 to be, we'll pick 1 for the second position, and the first position would be -5 times that, so we'll pick the vector -5, 1. We have our y2 is therefore -5, 1 times e to the 2t. Next up, we need our general solution. So we have general solution. Y is equal to c1 times the vector 1, -2 times e to the -7t plus c2 times -5, 1 times e to the 2t. Once we have our general solution, then we can go ahead and solve the IVP. So scrolling back to the beginning of the problem, we were told that y of 0 was the vector 7, 4. Y of 0 is the vector 7, 4. And this would be c1 times 1, -2 plus c2 times -5, 1. So we are essentially solving 1, -5 for our first row, -2, 1 for our second row, times c1, c2 is 7, 4. So we are solving the augmented matrix 1, -5, 7 for our first row, -2, 1, 4 for our second row. If we multiply the first row by 2 and add row 2, we wind up with 1, -5, 7 for our first row, 0, -10 plus 1 would be -9, and 14 plus 4 is 18. So we would have 0, -9, 18 as our second row. This means that C2 would be -2, and then C1 plus -5 times -2 should equal 7. And we wind up getting that C1 is equal to -3. So our final solution is therefore y is equal to -3 times the vector 1, -2 times e to the -7t minus 2 times the vector -5, 1 times e to the 2t. So this is how we can go about solving either for the general solution or solving an IVP in the 2 by 2 case. In the next video, we will look at the 3 by 3 case.